Engineering is all about pushing limits. We're always trying to go faster, further, and higher. But we can't do that without the right materials. Choosing the wrong stuff can be catastrophic. Remember that time I crashed the vampire dragster? Yeah, that wasn't fun. Every material behaves differently under stress, temperature changes, and fatigue. Imagine building a plane with materials that can't handle the pressure changes at high altitudes. That's a recipe for disaster. That's why understanding material properties is like knowing your engine inside out. It's fundamental. Take airplanes, for example. They need lightweight materials to soar through the sky, but those materials also have to be incredibly strong to withstand the forces of flight. Then there are cars, which require materials that can absorb impact energy in a crash, keeping the occupants safe. And let's not forget ships, which must resist corrosion from saltwater while carrying heavy loads. Understanding material properties isn't just about knowing what a material is made of. It's about knowing how it will behave under pressure. Literally. Let's talk stress. No, not the kind that makes you want to pull your hair out. The kind that engineers deal with. Stress is how much force a material experiences per unit area. Think of it like this. If you're trying to squash a marshmallow with your finger, you're applying stress. Strength is a material's ability to resist that stress. A steel bar, for instance, can handle a lot more stress than that marshmallow before it starts to deform. And then there's thermal expansion, which is how much a material expands or contracts when the temperature changes. Ever notice those gaps in concrete sidewalks? Those are there to accommodate expansion and contraction caused by temperature swings. In our world of planes, cars, and ships, these properties are crucial. An airplane wing, for example, experiences massive stress during flight due to air pressure and aerodynamic forces. The materials used in the wing need to be strong enough to handle these stresses without bending or breaking. Now, wouldn't it be handy if we could predict when a material was about to fail? That's where static failure theories come in. These theories help us determine the maximum stress a material can handle before it gives way. One of the most important theories is the von Mises theory. It's like the Sherlock Holmes of material failure, helping us predict when a material will yield or permanently deform under complex stress conditions. And then there are stress concentration factors, which tell us how much stress is amplified at corners, holes, or other changes in a material's shape. Imagine designing a car chassis without considering stress concentrations. You might end up with weak points that could buckle under stress, putting passengers at risk. Static failure theories are our way of making sure that doesn't happen. Section 4. Fatigue failure criteria. The long and winding road to failure. Things break. It's a fact of life. But sometimes they break after repeated stress, even if that stress is below the material's yield strength. This is called fatigue failure, and it's a sneaky culprit. To understand fatigue, we use tools like SN curves, which show how many cycles of stress a material can withstand at different stress levels. The Goodman diagram helps us predict fatigue failure under combined stresses. And then there's Miner's rule, which allows us to estimate the remaining life of a component that's been subjected to varying stress levels. Think of an airplane fuselage, constantly experiencing stress cycles during takeoff, flight, and landing. Over time, those cycles can cause microscopic cracks to form and grow, eventually leading to fatigue failure. By understanding fatigue criteria, we can design aircraft that can withstand these cycles for a safe operational life. Section 5. Manufacturing and beyond material properties in action. Understanding material properties isn't just for engineers designing these incredible machines. It's crucial for the people who build them too. Manufacturing processes like welding, casting, and forging can significantly influence a material's properties. For example, if you weld two pieces of metal together incorrectly, you might create weak points that are prone to failure. Choosing the right materials and manufacturing processes is like tuning a high-performance engine. It's all about achieving optimal performance and safety. Whether it's a supercar, a jumbo jet, or a cargo ship, the right materials are the foundation of every amazing feat of engineering. So next time you marvel at a technological marvel, take a moment to appreciate the hidden world of material properties that make it all possible. Because without them, we'd be stuck with a bunch of marshmallows and dreams. And that's not very exciting, is it?